address decoder designed for SRAM. Okay.
Yes, sir. Yes, sir.
So method of low power, high performance. So what do you mean by low power and high performance?
By using less power, we can get high performance.
Yeah. So performance in the sense here. So that is nothing but the power multiplied with the delay. So this gives our performance.
Okay.
Okay. So whatever, if we are going for the new one, something new one, new circuits, so the power is getting reduced and delay is getting reduced. So both are getting reduced, then the performance will automatically get better. Okay. So that is the one thing we are working on this project. The next, and also we are working on the area efficient too. Area efficient in the sense, nothing but transistor. Okay.
Okay.
So we are working on the transistors even. So like we need some less transistor, the count of transistor. Okay. And one thing in VLSI project, whatever it may be, so we are working on the three main parameters or three factors, you can say: power, area, and delay. So most of the most of the projects, they work on any two field, like power or delay, power or area, because there is no such a circuit or such a project. So all the power, area, delay, everything is getting reduced. Because some might means like suppose power and delay is getting reduced, but area might increase. Okay.
Okay.
Or might decrease. So we don't know. Okay. But we can decrease the area. Okay. So
Yes.
by how, in the sense, by we can change the logic, or we can do something like in paper, you see, there is NAND gate given. So like decoder, by use of NAND gates, they have given NAND gate and gates like that. So if we design, suppose AND gate with CMOS technology. So CMOS design, that is by using PMOS and NMOS. So we need 6 transistors. Okay. And now here in paper, AND gate is designed by using 3 transistors. Got it? So 3 transistors. So that is with 2 types of techniques they have given. So that is, I think so. One thing is, you can see here in our paper, that is TGL, transistor gate logic. So no, transmission gate logic. Okay. So
Okay.
this is one thing, transmission gate logic. So next thing they have given, that is uh, dual value logic. Okay. So dual value logic. So by using this transmission gate logic and dual value logic, what they are doing, they are designing the whatever the required logic we need. So I need required logic, that is AND gate, or otherwise OR gate, otherwise XOR, whatever it may be. So what is this? This is just nothing but arrangement of our transistors. Okay. So in transmission gate, dual value logic, what we are doing, we are making some arrangements of transistors by giving some input. And why we are doing that? For getting us required output with less number of transistors. Okay.
Okay.
So
Required
some,
output by less number of transistors.
yeah, less number of transistors. Okay. Nothing but the count is getting reduced. Okay.
Okay.
The transistor count. Now what we are doing again, if you see, uh, for as an extension part, so in paper they have given like transmission gate logic, dual value logic. Now
Okay.
next one, as an extension part, we are doing like GDI technique. GDI technique.
GDI means, sir?
That is gate diffusion input.
Gate diffusion input.
Yeah, diffusion input. So,
Input.
so what I'm doing, so this is has been done with the means implemented in the paper. So something new I have to do it. So we are using this technique. So that is gate diffusion input
The
technique.
extension is gate diffusion technique, which are using we
Yeah,
are the whatever logic we are using here, technique we are using is for extension gate
yeah,
diffusion.
gate diffusion technique. Okay.
Okay.
So what will be done in this technique? So now as you see, so here 3 transistors has been used. Okay.
Okay. Hmm.
So with this, we can use only 2 transistors for AND gate. Means again 1 transistor is getting reduced. It means something like power consumption for the 3 transistor will be more as compared to the 2 transistor, is it?
Yes.
Okay. So again like delay also will get it reduced, counts also will getting reduced. So it means we are going on the correct path. So that is what we are implementing. Now with this, how to implement the logics? So what logic? So that is logic and logic or all those things. Okay.
Okay. Sir, yeah,
So
again, come again, no, sir. From here, 3 transistors are used for, but we are reducing in this technique to 2 transistors.
2 transistor. Two
By that,
transistor.
if we
Ah,
are reducing the 2 transistors, by
hmm.
for that we gate delay also is reducing and count also is reducing. Is
Yeah.
correct, sir?
Yes. 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 Okay.
Hmm.
So now you got what is going to be decreased, what is going to be reduced here. Okay.
Okay.
Now how we have to design that? So
Here
here,
area also will decrease, sir. Sorry, sir. Sorry to interrupt. Here area also will decrease.
yes, see here 3 transistors are there, then 2 transistor area we have to means like we have to take in terms of transistors count itself.
Okay.
Okay. So here we can means we are taking area in terms of transistor count.
Transistor count. Okay.
Okay. So now one thing is that how we have to design these circuits, how we have to get these logics. Okay. So we got to know that. So this is the technique we are using 3 transistors. This is the technique we are using something 4 transistor. Now our extension technique we are using 2 transistors. So let us see now how we have to do that thing. Okay. So in GDI,
Excuse me, sir. Sorry for the interruption.
yeah,
Can I talk? I'm Nitya, sir. Sir, just now you have said regarding RNS and LNS. You'll be
yes,
explaining tomorrow 6:30, no, sir?
yes, yes, yes.
Yeah, good. Will you when will
Hmm.
you share the link, sir, regarding that?
You so how you are creating this link?
Hello.
Sir,
Same link only.
same link only, sir.
Same link only. But what time you join, ma?
Sorry, sir. I could not hear you.
And which time you will be joining and again? Yeah.
I'll
Yeah.
be joining by morning 6:30, sir. Just now, sir, I have given the time at 6:30, no, sir, in the morning.
We can, same timing only. Same link only, ma. Okay.
Yeah, okay, sir. Yeah, sure.
That time
Yeah.
will be possible, sir.
Yes, sir. Of course.
Thank you. Thank you.
Yeah, okay, sir. Thank you so much, sir. Sorry for the interruption. One second.
Not an issue. Okay.
Okay, sir. Thank you, sir.
Okay. So can I continue my class here?
Yes, sir. Yes, sir. Sure.
Yeah.
Start.
So where we are in the sense how we have to design the logic gates by using the GDI technique. So let us see how we have to now see. So as you know, a multiplexer. You know multiplexer?
Yeah, much we call it as much. Yeah.
Yeah, we call it as mux. So mux 2x1. How it is?
Two
So
inputs.
one, yeah, 2 inputs. So this is 0th pin and this is first pin. Okay. And next here, this will be like A input and this will be like B input. And next, this is my selection line. Okay.
Okay.
So this is the mux. So what I am doing in GDI, by the help of this mux idea itself, first thing what I am going to do is one PMOS. I am taking one PMOS.
PMOS.
Okay. Yeah, PMOS.
Okay.
Then next, another thing, I am going to take one NMOS.
Okay. One PMOS and one NMOS.
One NMOS.
Because
Now you
of,
see,
in place of MUX.
yeah, in place of mux kadu. So as a idea of, by taking the idea of mux. Okay.
Okay. Idea of MUX.
What we are going to implement is GDI AND gate, means AND logic by using GDI technique. AND gate. Now we have to get AND. So what is that? Means suppose we are having inputs 0 0 0 1 1 0 1 1. Okay.
Yes.
So 0 0 0 1. So this is what we are getting output for AND logic. Now we have to get that by the help of these two transistors. I said that, so we are using two transistor only in the GDA. So let us see how we have to do that. Okay.
Okay.
What? So here you can see mux is having like one selection line, two inputs A, B. Okay. So it is like this. So what I am doing, so I am sorting these two inputs, gate voltage inputs. I am sorting it as a selection line. Got it?
That's it.
Okay. Now you can see 0th pin. Okay. So this is, I am considering it as a 0th pin.
Okay.
Okay. Means here I can give any input over here at this point. Okay. At this point. The next, first pin. So I am considering this as a first pin.
Okay.
Okay. First pin. Now let us see. So now one thing what I need to do is, first I have to implement AND gate by using mux. So మనం mux తో ఒక AND gate ని డిజైన్ చేస్తున్నాం. సో ఎలా అంటే ఏదైనా gate, logic gate or whatever it may be, circuit, if we are going to design with the help of mux, then we are going to make a suppression of 4/2. Okay, because 4 combinations are there, 2 bits means 2 combinations will get separated. Okay. So now this is my A, this is my B input. If you see, my first two inputs are 0 and second two inputs are 1. Got it?
Yes.
Okay. Next, if you observe my output, so this is my output. This output is same as A inputs. If you just see.
Yeah.
Got it?
Yes.
So in the sense, at 0th pin, okay, means nothing but here at 0th pin, we have to take our input as A. Okay. Then next, now whenever A is my 1 1, so both the inputs are here 1 1, is it? So if you see now, if you observe the outputs, it is as same as B. It is as same as B. Just see, output is 0 1, B value is also 0 1. Got it?
Output is
So
0.
yeah. Okay. So then in the sense, at first pin I am taking B. Okay.
Yeah.
Got it? Now what I am taking as selection, so selection I am taking as a itself, because I am having two inputs itself. So selection also I am taking as A itself. Got it? Okay. So now what is my S? A. I am going to substitute the values. That's it. A. On 0th pin, A. Okay.
Okay.
On first pin, B. So now with this we will get the output. So let us see. Okay. So suppose I will take like 1 0 value. Okay. So this one. Okay. So A is 1. A is 1 in the sense, here it is 1, here it is 1. Then next, B is 0. So here it is 0 and here it is 1. Okay. So 1 in the sense which transistor is getting on? NMOS.
NMOS.
So at NMOS source value is 0. This is the 0. Okay. So which is going to the output. That's it. Nothing but here I got output 0. Got it?
Sir, once again, sir, come again. This point, I did not get this point.
Yeah. Okay. Not an issue. Just check. See. Now, again, I will go it.
Yes.
Suppose one second.
Yes, sir.
Now see, I want output for this combination 1 0. A is 1, B is 0. Okay.
Okay.
So now I am giving my A. 1 minute. A is 1 here.
Okay.
Means one is going for the PMOS and one is going for the NMOS.
Yeah.
Okay. And now what is my B value? B value is 0.
Yeah.
So B value is 0. So I am taking my B value at first pin. So that is 0. Got it?
Yes, sir.
So now here at 0th pin, again it is A value itself. So A in the sense 1 itself.
1 0. Yeah.
So which transistor will get on? So that is NMOS, no
Okay.
PMOS. Hey, see.
Yeah, that is 0. This is, yeah.
You know, see, whenever we give gate voltage as a 0 for the PMOS,
Okay.
0 for the PMOS, then PMOS will get on.
Okay.
PMOS will get on. And whenever we give 1 as a gate voltage for the PMOS, PMOS will off.
Off. Okay.
Okay. So this is the condition.
Okay.
And in vice versa for NMOS.
Okay. If for 1 it will be on.
Ah,
and
one it is on. So 1 it is on. And 0 is off.
Okay. Yes, sir. Got it.
Got it?
Yes, sir.
So now that is what we are doing. So here the input is 1, which is going for the PMOS and NMOS. So PMOS will be off, means there will be no flow.
Okay.
And now here it is 1, which is going for the NMOS. So in the sense there will be a flow.
Yes.
So whatever the value, it is going for the output. So what I got, so what is getting here? 0 is traveling to the output.
Output.
Output is 0. Like that we have to consider.
Okay.
Okay. So next I will give another simple example so that you can understand everything. Okay. So let us see OR gate. So OR gate, we are having same combination 0 0 0 1 1 0 1 1. This is my A, this is my B.
Okay.
And now I am having a marks like this. So this is a selection line. I won't write any name here. I will just give like this pins 0 1. Okay. So you just tell me at what means, suppose at this line what I have to get, at this line what I have to get, at this line what I have to get. Okay. So let us, and that we are going to implement, means substitute the values over here. That's it.
Okay.
So let us see now. So my OR output is like this. So when any one of the input is 1, output is 1.
1.
And if both the inputs are 0, output is 0.
0.
Now we are going as a concept of mux kada. So
Yeah.
it means we have to make a separation of two combinations.
Yeah.
So whenever A is 0 0, okay, and you can see 1 1, okay. So whenever A is 0 0, so how my output is, so if you see my output is 0 1, which is just equal to B.
Yeah.
Got it?
Yes.
So at 0th pin, if I consider A as my selection line, at 0th pin I have to take B value. That's it.
Yeah.
Okay. Now if you consider at this point, whenever my inputs are 1 1, so how is my output? It is
1.
as similar to A.
Okay.
See, 1 and 1 and 1 and 1. Okay. So in the sense, at first pin we have to connect A. That's it. So in this diagram by here, so here A, and here B. That's it. So we will get a OR logic.
Yes.
Got it?
Yes, sir.
So like that we are implementing. Now what I have done, so already this circuits has been given in your paper. If you see, you got it, GDA.
Yes.
Okay. So then here past transistor circuits has been given here. You can see from this. So you can see TGL AND gate is there. Okay.
Yes.
So from this I am getting a AND logic. So how, in the sense, suppose if we take like, see here, so you can get it that like this is a PMOS and this is the NMOS. If bubble is there, that is a PMOS. Got it?
Yes.
What we will do here, just by giving some input, we will let know whether it is an AND gate or not. Okay. So here it is given like VSS. So what is VSS? So that is 0 here.
0.
Okay. So then next, I'm having inputs like X and Y. So suppose X I have taken 1 and Y I have taken 1. Got it?
Okay.
So X is 1, which is going for the NMOS.
Okay.
Okay. So NMOS in the sense, this is on.
1. Yeah.
This is on. Okay.
Yes, sir.
Got it? So
Yes. Got it.
this one is on. Means suppose this Y, which is forwarding to the here at this point. Okay.
Yeah. Output is 1.
So which is directly getting it to the output. So yes, whenever my both inputs are 1 1 in AND gate, my output is 1.
1.
I got it. You can check all those combinations, not to worry. Okay, we will get the AND logic. So
Yes.
like that you can check here OR logic. Okay.
Yes.
So just by giving just input, so here suppose like VDD. So what is VDD? VDD is 1. VDD is nothing but constant. Okay.
Yeah.
So now what is Y? Let us see. Suppose if I am taking X is 0 and Y is 1 for OR gate.
Okay.
So what is the output? 1.
1. 1.
Okay. So Y I am taking, so X is 0. So 0 I am taking, Y is 1. So 0 is going for the PMOS. Nothing but
Yeah.
on.
Oh, yeah. Yeah. On. Yeah. Yeah. Yes.
Okay.
Yes.
So then in the sense, Y, whatever Y value is there, so it is traveling to the output. That's it.
Okay.
Got it?
Yes, sir.
So like that. Now these things, whatever the circuit they have given, by the help of this, what we are going to do, we are going to design a decoders.
Decoder, sir.
Okay. So what is the decoder, you know?
No, sir.
So decoder is a combinational circuit.
Okay.
Decoder is a combinational circuit. Got it? So which is having n inputs and 2 power n outputs. So this is the definition of a decoder.
Okay.
So this decoder circuit we are going to designed by the help of the whatever the whatever the logics we have designed now. So that is TGL, DVL, the next GDI technique. So by the help of these three techniques we are going to implement. Okay.
Yes, sir.
Next. So GDI is one our extension. Got it?
Oh yes,
So,
sir.
then next here, suppose if n equals to 2.
Okay.
If n equals to 2, then my inputs are how many inputs?
Two inputs.
Two inputs. So suppose what we will do here, we will take it into the snipping itself because we can write here.
Okay.
So n equals to 2 in the sense I am taking inputs like this. So I of 0, I of 1. Okay. If you want AB, you can take AB also. So let us see with AB. So how we can do that? So variables we can take with our own, not an issue. Okay, A, B, I am taking like this.
Okay.
So whenever two inputs are there, as we know, 4 combinations: 0, 0, 0, 1, 1, 0,
1,
and 1, 1. So now output for this will be 4 outputs, 2 power n kada. So
yes.
n is 2. So 2 power 2 is 4. Okay.
4.
So I will take like this outputs: A0, A1, A2,
A3.
A3. So if you see this 0, 0 is nothing but in decimal it is 0 value.
Yes.
0, 1 in decimal 1. 1, 0 it is 2. 1, 1 it is 3.
3.
Got it?
Yes.
So now from this first input is 0, 0 kada. So
yes.
it means 0th pin is enable, A0 is enable, and the remaining are zeros. The next here 1. So first pin is enable,
rest are 0.
Rest are zeros. Azun arda tas. So the next 2, 0,
A2
1, 0, 0. The next 1,
0, 0,
0, 0. Got it?
Yes.
So that's it. So this is the decoder. Now, if you take a equation for A0, so if you take a equation for A0, so A0 is equals to, that is A bar, okay, A bar, B bar, because it is enable at this C, 0, 0. So here 0 indicates bar. Okay, so 0 indicates variable bar and 1 indicates only variable, like this. Okay, so whenever we are taking the equation of A0, so it is enable at 0, 0. So that is nothing but A bar, so dot B bar, A bar dot B bar.
B bar. Okay.
Yeah. What is that dot? Dot is nothing but AND operation. Okay.
Nice.
Good. Then next A0 is completed. Then next let us see the that is A1. Okay. So A1 will be, means it is enable, this is enable at 0, 1. So now how can I write this? So 0 I can write it like A bar and 1 I can write it like B. So A bar dot B. Okay. Then next A2. So next what I have to do? So what is my equation? So it is enable at 1, 0.
Yeah.
A B bar. Then next A3.
A3. A bar, B bar.
No, AB.
Okay. Yes.
It is 1, it is 1.
Yeah, yes.
So 1, 1. So if you see from all the outputs, the common thing is AND logic. Is it?
Yes.
Means dot product is nothing but AND logic itself.
And logic.
So AND logic we have designed with the help of extension also, and with the existing one also.
Okay.
So that is what we are going to implement, and we are checking the results. Okay.
Okay.
So now if you see, I have done all the circuits over here. So so as you know, you are having a Tanner software. You know Tanner software?
Yes, sir, but I'm not used to that.
So okay, you have not used that. Okay.
Yes,
So
I'm not used to that. Yeah.
okay. And so not to worry.
Why? Because basically I was from electrical background, so
Okay.
directly MTech I have taken from this.
Okay. So it's easy one itself. So you can get, so if you are means whenever you are having time, you just go for the YouTube videos. It is easy how they will give like how we have to create a inverter in this, all those things. But I will let you know here. Just see. Okay.
Okay, sir.
So first thing, I will show you that what we have implemented. So you can see here 2 to 4 decoders, 2 to 4 decoders. This is the thing we have done here. So here you can see GDI decoder, even the GDI decoder. So just simple, everything we have done here. So whenever you go and run here, so you will get into simulation. So let us see, suppose if I am going for the GDI decoder. So what we have to do, only we have to see here, start simulation.
Okay.
So it needs some time to load it. Okay. So let us see here. So one minute. So here, if you see, we are having time period up to 10. Okay, this is 1, 2, 3, and 4. What is?
Yes, sir.
So means up to 4 combinations we have taken. So let us see combinations. So A is 0. So A is 0 and B is 0. Okay.
Yes.
Then A is 0, B is 1. Then next A is 1, B is
0.
So A is 1, B is 1.
1.
Okay. So now we got the combinations in waveform. Now, whenever we are having 0, 0, our D naught is enable and rest are 0. You can see here.
Okay.
Got it? So then next, whenever 1, 0 is there, our D1 is enable and rest are zeros. Okay.
Yes, sir.
So next, whenever 1, 0 is there, then 0, 0 and D2 is enable, rest are zeros. And whenever 1 is there, so all are zeros except D3.
D3 is enabled.
That's it. So it means we got the output. Okay.
Okay.
Now let us see. Okay. So this is what about the simulation. So if you run or whatever it may be, like we are having these files 2 to 4 decoder, 2 to 4 decoder by using inverter. So all those things are there. Okay. So
Yes,
by the help of 2 to 4, we can design 4 to 16 also. But now what we are going to implement, so we got output. So even if you run all those things, you will get the output, not an issue. So, okay. But the thing is that why we are doing this project? For the power consumption. So let us see. So whether we are getting or not. If we are not get, then again we have to work for the extension. Okay.
Yes.
Got it. So let us see. So these 2 to 4, whatever the HP is there, so it is my previous one. So whatever given in the means like whatever given in our base paper. You can see these diagrams itself I have just designed over here.
Okay.
Got it. So how I will design, how we have to design, I will let you know by giving you like CMOS inverter, by designing a simple CMOS inverter. Okay. So then just see here. For this, what you have to do now, I want to check the power consumption for this circuit. So just click here.
Okay.
So 1 minute. Yeah. Just 1 minute. I will just close, and once I will open that.
Okay.
So 224 HP high power consumption. So that is now what I am doing. I am going to open a T-Spice. So you will get another software, that is T-Spice. Okay. So means here we can see. So as you see here, so what are our voltage sources, input voltage sources? So those are VV1 and VV2. So simple one line code is there, that is dot power, okay, VV1. Okay. The next dot, 1 minute, dot power
VV2.
VV2. That's it. Save it and next run this. So 1 minute. So we have to change the library. So just wait. So open in T-Spice.
Okay.
So it is opened here. So again we have to write the code, that is dot power VV1
VV1.
dot power
VV2.
VV2. Control S, that is save and run. So done here. So already we have went for the waveforms, no need to go. Now you can see here what is your power here consumed. Okay.
Okay.
So suppose what I will do, I will just copy it in the notepad and let us see. So for VV1,
Yes.
this node needed and these 2 points no need. So for VV1, our average power consumed is 4.71.
Okay.
Okay. So that is E minus 005 in the sense exponential of minus 5 watts.
Yes.
And here VV2, our average power consumed is 4.30. That is same E005. Now what we have to do, we have to change this into microwatts. So if I want to change this into microwatts, so this becomes 47.16 microwatts. So microwatts in the sense 10 to the power of 6 microwatts. Then next here, this is 43.071 microwatts. Done.
Yes.
Okay. So now average power consumed by the total circuit is 47 plus 43. You have to do it and you have to make the average. So divide by 2. Got it?
Yes.
That is our power consumption for the, that is existing one.
Okay.
And next, let us see the proposal, that is GDI. So again, what we have to do? So just close this all. waveforms and all those things, just open with SEdit. Okay, so now go for the GDI decoder, then next open with the T-Spice. Okay, now same thing. So we are having here A, that is VV3, and B, that is VV2. So dot power VV2 dot power VV3. Save it and run here. So if you see now here, I got this. Control C. Okay.
Okay.
Here I am copying it. Okay. So these two lines no needed. So now it is already, we got in the e power of -6, exponential of 6 in the sense microwatts. So
Yes.
directly what we got output is 9.2.
928.
So 9.2 microwatts, and next we got 6.8 microwatts.
Yes.
6.8 microwatts. So when we add, see, you can see the difference here, 47, 43 and 96. So whatever we got means whatever we have done the extension, that is perfect.
Perfect. Yeah, it is reducing.
So that is the thing. So next, here you can see the number of counts. One. So MOSFET, 1 minute. Oh, here it is given like MOSFETs 12. Okay. So 12 for that is GDI one. Okay.
Okay.
12 for GDI. So let us see for the existing one. So which I have not seen before. So once again I have to close this, and next again I have to run with this 24 HP and run this with T-Spice. So by the basis of this, we can go for like for the like 4 to 16, then next like 5 to 32, all these decoders. Okay. So just I will run it. So then you can see here how many transistors are there. So here we are getting like 15. Okay. So MOSFETs are 15. What we got here, that
12.
is 12.
Yeah.
So of course, again we are getting decreased. Okay.
Yeah.
So this is what we are going to prove in our project.
Yes.
Got it?
Yes.
So next, now I will show you like how to like design a PMOS as a CMOS inverter in this. Okay. So first thing, you can see the menus options. So file, edit, view, draw, cell, all those things. Okay. So from this file, what you have to do, you have to take a new design. Okay. So whenever you take a new design, so whatever you give your new design name, and then select your path. So where you want to start. Okay. So just click OK. So already I have created, that is my project name is 2 to 4, 4 to 16 decoder. Okay.
Okay.
So the next thing here you can see add. So from this you have to add the libraries. Okay. So whenever you install whatever the Tanner, okay, Tanner software, in documents you will get the libraries, all the libraries. So in documents, Tanner EDA, you can see all the libraries over here. Okay. So these are the libraries. So generic 250, we have to take the library. Okay. Got it? So next thing, after taking that, we have to take a cell, new cell. Okay. So suppose this cell, I am writing it as a inverter. So click it. So I will get this black screen display. So how I can design CMOS inverter? By the use of one PMOS and one NMOS.
Yes.
So go to devices. So in these devices you can see PMOS and another NMOS. So just we have to take PMOS and NMOS. Now here it is given like wire, so you have to wire it up. So and this thing we have to sort it, and which we have to give to the input, and this here we will get the output. Okay.
Okay.
So here's ports are there, so input port. So when you click R, it will be rotated. Okay. So just input. So I am giving like IN output, OUT out. Okay. I'm not changing anything. So then next here you can see we have to give the VDD. Here we have to give the ground. So in this MISC we are having like ground. Done. Then next VDD. Done. Okay.
Okay.
So now it is completed, means the schematic diagram has been completed. Now we have to take the supply, voltage supply. So how? Here you can see in spice elements. So we are having voltage supply. In this voltage supply, one voltage, that is bit of 9, is connected to input. And another supply voltage, that is DC voltage, is connected for this one. Okay. So here you can see negative, positive and negative are there. Negative is connected to the ground. Again, negative is connected to the ground here. And this is also my so here what I am giving is this is the VDD source. Okay. So when you click this, so here it is like pattern. Pattern means giving the input sequence. So I am giving my input sequence 1 0 1 0 like that. Okay.
Binary.
Yeah, binary itself. We have to give binary itself. Okay. So then next go to setup simulation. So before going to simulation, so you have to print your input and outputs. So that can be done with the help of this command. So there is a print voltage command. So one thing you have to join it in the input, another thing at output. That's it. Okay. So now go for the setup simulation. So in that transient Fourier analysis, in that select the stop time. So I am taking 40n, and here I am taking something like 1n step time. Then next in this general, so must and should for getting our output library is needed. So that is generic 250 library. Okay. So, okay. Then next at last we have to take space caps lock TT. Done. Okay. Okay. So now you are able to run this. So let us see. After saving, you can run this. Okay. Just once it is saved, you can run. So just go for the green button. This is the green button. So run it. Okay. So you can see what is my input. Input is 1, output is 0. Input is 0, output is 1. So like that, we are getting the inverter. So like this, we are just designing all the logic gates. Got it? Yes. And all the circuits also, means depending upon this idea itself, we are doing just nothing but drag and drop, connect it. That's it. Okay. Got it?
Okay, sir. What is the x and y axis, sir, in this?
Which one?
In this graph.
This is voltage. This is time.
Okay.
Okay. Y axis. If you take y axis as a vertical. Okay.
Okay.
So that is time. That is voltage. Sorry. Like 0 voltage, 1 voltage, 2 voltage, 5 voltage. It is given like this. Okay. And here you can see time. This is 0 nanoseconds, 5 nanoseconds, 10 nanoseconds. This is x axis. Okay. Okay. So this is all about our project. Yes. Got it? Any doubts are there?
Got it, sir. Clearly.
Okay, so I will send this file to your mail, and even the Shiva sir, they will send to Mahesh sir, so you can collect your files. Okay.
Yes, sir. And documents, sir, regarding this?
Yeah, even document also.
Okay,
In that,
sir.
all files in the cells, all the things.
Okay, okay, sir.
You will get there. Okay.
Okay, sir.
Okay. Then. So can we end up this session here?
Yes, sir. Sure.
Yeah. Thank you.
Thank you, sir. Thank you, sir. It was very nice.
Thank you.
So Mahesh sir.
Sir, yeah, tell me, sir.